for us. So now we want to talk about orientations. Let's consider a one simplex that is given by this line. Let's say this is P0, this is P1. Now you can write it as P0, P1 or P1, P0, and both of them are correct in this case. However, if I tell you that I want to give some orientation or a direction to this one simplex, let's say from P0 to P1 like this, then these two terms are not equivalent. So in such cases we say that the simplex has some orientation. So since this simplex, this one simplex, has been endowed with an orientation, and in this case you can also think of it as a direction, we say that in this case P0, P1 is not equals to P1, P0. Rather, we want to distinguish them. And we can do that by just using the idea of directions, that if you consider going from P0 to P1 as a positive direction, let's say, then you can consider going from P1 to P0, which is in the opposite direction of the initial path that you took, think of it as a negative one. So going from P1 to P0 would be negative, and going from P0 to P1 would be positive. So we can write it as this: P1, P0. I want to make a comment. The notation used in some literature to denote oriented simplexes uses the round brackets. That is, if I write it like this, then this means there is some orientation, or the simplex is oriented. There is some sort of a orientation that is given to the simplex. There is some sort of orientation. Okay, but for us we will stick to this notation. And whenever we are dealing with oriented simplexes, we will mention that explicitly. So we mention explicitly whenever we are dealing with oriented simplexes. Okay. Now, let's say instead of a one simplex, you can have something like this. So this is another example. Let's say P0, P1, P2. Again, we are dealing with oriented simplex. And if you want to draw this out, it would look something like this: a triangle, P0, P1, let's say, and this is P2. And I want to give it an orientation. Let's say I take the counterclockwise direction as my orientation. That means if you start from point P2, let's say, first you have to go from P2 to P0, then from P0 to P1, and then from P1 to P2, like this. Okay. Now I can write this as minus P0, P2, P1, like this as well. Why? Because what does this mean? This box meant that if you start from P2, you can go to P0 and then you can come back to P1. Okay. Or similarly, you can think of it like this, that the first thing, that means the first thing that comes here is the P0. So if you start from here, P0, then you go to P1, and then you go to P2, and then you from P2 you can go back as well. However, with this description in mind, look at this guy. It says, oh, start from P0, but then you go to P2. But that direction is opposite to this orientation, right? The given orientation, so you pick up a minus sign. So that's why you have a minus sign in front. However, even though it might seem a bit confusing that in which way you are going and you are trying to relate this intuitive way of going from one point to another to this simplex notation, it might get a bit confusing. So a rule of thumb is that whenever you are dealing with oriented simplexes, the cyclic and the anticyclic permutations come in different signs. So one way to think of it is to just remember the mnemonic that whenever you have 2 points adjacent to each other like this, let's say P1, P2, you interchange them and you pick up a minus sign. So in general, let's say you have a n simplex like P0, P1, P of n. This is related to this P0, P1, P of n. We may or may not interchange the indices in or the entries in between. Let's say we can interchange P2 to P with P3 and so on. So we don't mention that inside this. Rather, we take that into account by introducing a sign times this thing, and this sign is given by the Levi-Civita symbol, or so to say the permutation symbol. Okay. So again, let's see this triangle example again and see which are our cyclic and which are our anticyclic things. So let's say we start from P0. So from P0 we can go to P1 and then P2. So this is P0, P1, P2, like this. Then we can start from P1 as well, right? So if we start from there, we can go to, first we start from P1, then we can go to P2, and then we can go to P0. So P1, P2, P0. And then we can start from P2, we can go to P0 and then P1. So P2, P0, P1. And this is equals to equal with a minus sign in front is given by, let's say I start from P0, I go into the totally opposite directions like this one, and this one. So let me use the red color to indicate that. First I go from P0 to P2, I pick up one minus sign. I go from P2 to P1, I pick up another minus sign, and then finally I go to P1 to P0, so I pick up another minus sign. So in total there are 3 minus signs, right? So it's nothing but minus 1 cube, which is just minus 1, and then I can write it as P0, P2, P1. And now you will realize that, oh, there it is. We saw this over here, right? And we can again start from P1, but in the opposite direction. I mean, not the opposite orientation. So now we can start from P2 or P1 over here, since we started from P0 in this case. So I can now again go from P1 to P0, because if I go from P1 to P2, I'm going along the direction that I initially gave or endowed this simplex with. So what I want to do, I want to go from P1 to P0 so that I can go into the opposite direction. Okay, so I go from P1 to P0, pick up a minus sign. I go from P0 to P2, again I pick up another minus sign, and then I go from P2 to P1, I pick up another minus sign. So in total minus P1, P0, P2, and the other term can be done similarly by starting from P2, and from P2 you go to P1, from P1 you go to P0. So this is just P2, P1, P0. Okay, so if you call this trio as the cyclic permutation, you would call this trio as the anticyclic permutation. Now let's have a brief look what does these two terminology mean. So cyclic permutation. So let's say you have 4 indexes like this, you have 4 points like this. Okay, let's induce a orientation, that means the anti-clockwise orientation, and we are taking this as a positive thing. So this would give us okay, let's take 3 points because 4 points would be a bit complicated. So this combination of A, C, D would be equal to C, D, A would be equal to DAC. So this is a cyclic permutation. And anticyclic is just the opposites of it. Anticyclic permutation is that you have again A, C, D, but this time you go to clockwise. That means opposite to this configuration over here. So you can write CAD equals to ADC, and then you can write DCA. And these two permutations, if I denote all this trio with this diagram and this trio with this diagram, then ACD, the cyclic one, all the elements of the cyclic one would be equal to minus of ACD with this elements of this configuration over here. This is a sort of shorthand notation for writing this. So this is what we mean by cyclic and anticyclic permutation. And now what we will see is that the tools that we developed, and we're going to develop some more tools, they will actually enable us to compute some interesting quantities. So now what we want to do, we want to develop some more tools, and we want to talk about the group structure of simplexes.